So we are discussing liquefaction of soil, and in the last class we discussed what is the constant mean and the extreme principal stress concept and how it applies. So in the last class we were discussing about liquefaction of soils, and we were discussing about the constant mean and extreme principal stress concept and how it applies to liquefaction of soil, and especially to the triaxial test that we do, cyclic triaxial test, to determine how liquefaction in a soil may occur. So typically there is a soil element. So there is a soil element, and when it is at a particular depth, suppose z, so we have the sigma z in the vertical direction and the sigma h in the horizontal direction. From the try to come on time because it disturbs the flow. Anyway, okay. So we were discussing. So we were discussing liquefaction of soils and the constant mean extreme principal stress concept, all right, and how it applies to uh, study of liquefaction, and how we apply that concept to the cyclic triaxial test that we do to study the liquefaction phenomena, to how understand how the soil will liquefy under various loading conditions. So we have a soil element at the depth z, and we have the sigma z and sigma h. So this is the initial condition of the soil, initial condition. So we have the sigma h and the sigma z, right, and we have a mean. So when there is a dynamic load, when there is an earthquake taking place, so what happens? So the shear waves, they travel in the upward direction. So that is what Seed and Lee 1966 they advocated. So when they move, when the shear waves move in the upward direction, so only things that changes, only stress condition that changes in this element is the shear stresses. So the shear stresses, once it acts in this direction, then it comes back, reverts back to the initial condition, then again it changes direction in the other direction. So again it reverts back to this initial condition, again then it changes to the other direction. So we have, from the constant mean state, we have an increase in the shear stress, then reversal up to the mean, constant mean, again there is a reversal in the direction. So this is one cycle. So this is the concept, means this is the mean, constant mean at this point, and these are the extreme principal stress. So basically when there is an earthquake, what happens is that, so this is sigma h and this is sigma v. So this mode circle, it grows. So there is an earthquake and it again comes back to the original position. Again it grows, again it comes back to the original position. So again it grows, again it comes back to the original position. So that is what is happening during an earthquake. So these are how the stress is varying in this element. So we saw how we can replicate that in the triaxial. So in the triaxial we apply the triaxial cell pressure, we apply the cell pressure, and then we apply the deviatoric load. So while applying the in the triaxial, what we can do is, obviously there will be cell pressure all around. Obviously there will be cell pressure all around the element in the soil sample. Then there will be pore water pressure within the soil sample, and there will be the effective stress in the soil. So when we apply the deviator load, we can change the values. We can increment the values from a zero value to a value which we require sigma d. So it increases to sigma d, again reverts back to zero, again it comes to sigma d, again reverts back to zero, again it comes to sigma d. So that is how we apply the cyclic load. All right. Now how, while applying this type of loading in the sample, how is this state, this increase and decrease of the Mohr circle while keeping the mean constant, being replicated in the triaxial test? All right, so we have the sigma d here. So what happens is that while we apply sigma d, so we have the, so here what we have is the initial confining pressure 200 kPa. So that means the cell pressure is at 200 kPa and the initial pore water pressure is 100 kPa. So the effective stress state in the soil is 100 kPa. So we have the effective stress and we have the total stress. Now when we start applying, so this is 200 kPa and this is 100 kPa. So when we start applying the deviator load, so it starts from 0. So it is the diameter of the Mohr circle here is 0. As we increment the deviatoric stress, so from 0 to 1 to 2 to 3, as it goes on increasing, what happens? The Mohr circle will develop. So this is the total stress Mohr circle, and here this point will remain constant at 200 kPa. So the Mohr circle will develop. So this is how the Mohr circle will develop up to sigma d. All right. So this is sigma 1 is equal to sigma c cell pressure plus sigma d. All right. So this is the deviatoric, maximum deviatoric load that we have applied. Now what happens is that when we apply this load, when we apply this increment, so there is a increase in the effective total confinement. There is an increase in the total confinement by half of the deviator stress at that point. All right. So here it is half of this. So here it is half of that. Again here it is half of the deviator stress. So that is the increment in the total confining pressure. So sigma delta sigma c. All right. Now considering the soil to be normally consolidated, so whatever delta sigma c will occur, same amount of pore water pressure will develop, or delta u will be equal to delta sigma c, which is equal to sigma d by 2 at that point, right, at that particular step. So what happens? Ultimately sigma dash remains constant. So there is delta sigma dash is equal to 0. So the mean, constant mean point is always preserved. Right? So constant mean, here we see the effective stress will grow at that same point. Alright. So as we go on increasing the total stress, so the total stress will increase from the 200 kPa point. Alright. So it will increase from the 200 kPa point, and it will, as the deviator load is applied, it will increase towards the right, whereas whatever change in the mean, total mean confining pressure is occurring, that amount of pressure is taken up by the increment in the pore water pressure. So what happens? The effective mean confinement remains at that same particular point. So the stress condition is preserved. So this is one cycle. All right. Now, so these are the more circles at different times of the cycle. All right. So at one cycle, in one cycle we have this more circle in one direction increasing and then coming again back to here, again going in the other direction. So there is a change in the direction. So now what happens? Now here we were talking about very slowly given increments of deviator load. So there is no increase in the pore water pressure. All right. So dynamic oscillation or dynamic vibration is not given as such. It is very slowly increased. So the mean effective confinement is exactly at that same point, that is 100 kPa. But when we apply the cyclic loading, so we see that there is two numbers of cycle within 1 second. So it is 2 hertz. The frequency is 2 hertz. Right. So when that amount of loading is applied, so at 1 cycle it increased to this maximum deviatoric stress. Then again it decreased to 0. Again it increased. So this is the total stress mode circle, and this is the effective stress mode circle. So what will happen when there will be now when it is applied dynamically, it is applied at a very high rate of loading. So there is increase in pore water pressure with each loading condition. So initially it started from 100 kPa of pore water pressure. All right, then at the final stage it reached 200 kPa. So basically then it sigma dash became 0. So what happened is that with each increment, all right, with numbers of loading, as we go on loading the soil sample dynamically, or there is the vibration being given in the deviator stress. So there is development of pore water pressure, and as there is development of pore water pressure, as we know, sigma dash is equal to sigma minus u. So the mean effective mode circles, all right, they will start moving to the left. All right, so it will decrease. The mean effective confinement will decrease because there is increase in pore water pressure. So ultimately it will move to the left. All right, and as soon as it reaches this point, all right, so it will start moving. So as soon as it reaches this point, so significant amount of strain will start developing in the soil. All right, significant amount of strain will start developing in the soil, and then we keep on loading, and ultimately at the particular point, all sigma stress, effective stresses will become 0, and that is the initiation of liquefaction. Right. So we saw that in the undrained condition, as in the in situ condition, this constant mean and extreme principal stress concept is also satisfied. So we have this constant mean, and the loading cycle only, the loading was applied only by increasing and decreasing of this Morse circle. All right. So this is the extreme principal stresses, and this is the constant mean. So this is the laboratory study done by Seed and Lee 1966, and that particular increment. So here we see there is an increment of sigma d by 2. So that is excess pore water pressure initially developed. All right. So that pore water pressure, what the researchers did was they corrected from the pore pressure measurement. So this is the measured pore pressure, using the instruments, and then that measured pore pressure was corrected for this particular value. all right, and we see that only after a numbers of cycles, some numbers of cycle, there is significant amount of strain, axial strain in the sample. So that is because it, as the pore pressure develops, so we have the loading like this, all right, and this loading goes on. So as the pore pressure develops, the more circle they start moving, and this is now it has reached a failure condition here, all right. It has reached a failure surface here, so there is huge amount of significant displacement, all right. And then at a particular point, all effective stresses are nullified, so we have a liquefied soil, all right. So the soil will now behave as a viscous fluid, and it will almost flow at constant shear stress. Okay, so we have to apply a constant shear stress at that state to make it flow, all right, to make it flow. So that is flow liquefaction. Now if we plot this condition in terms of P and Q, now we so P, we define it, in this case we define it as sigma 1 plus sigma 3 by 2, and Q as sigma 1 minus sigma 3 by 2. So this is basically the diameter here. So the radius here is Q, all right, and this point here P is that center of the Mohr circle is P, all right, and the radius here is, so this is Q. But now of course here it is tau and sigma, all right. So if I plot it in terms of, P and Q, what will happen is that the stress path will look somewhat like this, and it will go and oscillate in between these 2 points in this manner, right. We will see that how is this significant, all right, but try to just correlate between the P and Q plot and the Mohr circle plot. Okay, so we will see in the next slides why is this so relevant. So we have this test being done. So then again we saw the cyclic simple shear, all right. So same amount of loading was applied here. So contrary to the direct shear, so in the direct shear we had a plane of shearing here, all right, and this was moved, this lower part was displaced, and the reaction from the sample, was measured using the load cell, all right. So this is basically a strain control test. But we will see, we will define what is stress control and strain control just before going on to the steady state line. Okay, so in the simple shear we have a flexible kind of encasement, all right, which moves with the sample. So we have constant shear in the entire sample. So this is the sample. Again in the next part of the cycle we have in the reverse direction, shearing in the reverse direction. So this is the shearing occurring in the sample. So this is simple shear. So we see the development of pore water pressure, all right, and only after certain numbers of cycle, there is significant amount of shear straining developed, all right. So that means the pore pressure has to develop, and it has to lead to the failure, as we define the failure surface, all right. So the pore pressure, the Mohr circle will move to the left, and as soon as it touches the failure line, failure surface, all right, so there is significant amount of straining in the sample, and with that there is also development of pore water pressure, right. So as we saw, Casagrande in 1936, he defined that using the critical void ratio, if a soil is in a loose state, so in undrained condition it will develop pore water pressure, excess pore water pressure in the positive excess pore water pressure will be developed. So there will be a negative or decrease in the effective confinement. All right. So that soil is susceptible to liquefaction. All right. So if it is in a loose state, it has an undrained stress path in this direction. All right. And as soon as it reaches here, so we have a liquefaction. So that is was what was defined by Casagrande in 1936. Then we saw that of course that is not always applicable. So this sample A it liquefied and the sample B did not liquefy, though it is above the critical void ratio line. Right? As far as this definition, this should liquefy because this is the stress path. Right? But it did not liquefy, whereas this liquefied. So we will see how that is defined. Right? So yeah, going uh, further, we have to just look into two aspects. So one is what is strain controlled test and what is stress control test. Right? So basically in strain control test, what we do is there is a proving ring, right? And this entire sample is moved in the upward direction, right? And the reaction from the sample, the reactive load from the sample is actually measured in this proving ring. All right, so the sample is shearing at a steady rate, at a constant rate, and we have the reaction from the sample measured here. Similarly, here also this lower part of the direct shear sample is moved or displaced in the towards the right. All right, and we have a load cell placed here, and that load cell measures the reaction from the sample. Right, so this type of curves which we get, so here we see, so as the sample is moved, all right, as the sample is moved, so it reaches a maximum value, and suddenly there is failure in the sample. So what happens, this spring now pushes into the sample and the load in the spring is released, so we have a release in the load. All right, so this is called strain softening behavior. Of course, that part I think is covered in the stress strain chapter. So we have a strain softening behavior here, and ultimately there is a, when it is moved at a constant rate, all right, constant displacement is given, so we arrive at a constant deviator load from the, or a constant reaction from the sample onto the proving ring. So here also a constant, as it is moved, we have a constant reaction. All right, for this rate of movement, we have a constant reaction from the sample onto the load cell. So it is basically like a spring. So we have a spring attached to the sample. All right, so we measure compression in the spring. So we, from the compression in the spring, we measure the force, and from the force we divide by the area and we get the stress in the tangential stress in the sample. So similarly here also there is a spring and the sample exerts a load onto the spring and the spring compresses. So whatever the compression in the spring, we get the force, and divided by the cross-sectional area of the sample, we get the stress, axial stress, sigma A or sigma D, right? Sigma D in the sample. So initially the sample moves up, all right, as it moves up this spring compresses, it compresses, then suddenly what happens, the soil is unable to take the load anymore, all right, and the spring now compresses into the soil and the soil fails. So as soon as the soil fails, we have a strain softening part. Then when the soil is moving up at a constant rate, we have a steady load or steady compression in the spring measured. All right, so that is the deviatoric stress. Whereas in the stress control test, what we do is we apply the load according to our requirement. All right, so it is not based on the reaction from the soil. We apply the load, whatever load we want to apply, and we measure the strain in the soil. All right, we measure the strain in the soil now. So here you see there was no strain here. There was no strain here. Still, we were applying same amount of load. We were applying same amount of load. All right, but what happened? When there was significant amount of pore pressure developed, suddenly for that same amount of load, deviatoric load, there is significant amount of displacement or axial deformation. Right? So that is most of the cyclic triaxial tests. They are stress control tests. Of course, there are strain control tests as well. That is, I leave it up to you for further research and study. Right? So this is, of course, just an introduction to liquefaction, and we will continue with this. So then we came to the why we need to define the steady state line. All right. So we learned that when Castro 1969 he defined that when a soil is loaded, all right. So up to a point it will get loaded. So beyond that point, what happens? There is for a this is of course for a stress control test. Okay. So suddenly what happens? There is huge amount of strain, right? So if we plot the strain for up to this point, there is no strain at all right? So there is no strain at all. Maybe some amount of strain will be there, and then suddenly there is significant amount of strain being developed in the soil. All right. So in this manner also we can say like this. Right. So there is huge amount of axial deformation. So what when that happens, all right. So when that happens, there is excessive amount of pore pressure generation. All right. And then after a certain point, we will see that after a certain point, the generation in the pore pressure stabilizes, all right, and the deviatoric stress required to cause constant rate of deformation also we arrive at a constant value for a particular confining stress, effective confinement, all right, and then the soil constant at a constant velocity, it shears, all right, it shears at a constant velocity and constant volume, so no volume change, no pore pressure generation, all right. So that particular state was defined as steady state of deformation by Castro 1969. So to arrive at that, what he did, he tested three samples, right? So here P, so P is equal to sigma 1 plus sigma 3 by 2. So P dash is equal to P minus U. Okay? And Q is equal to sigma 1 minus sigma 3 by 2. So what he did, he tested three samples, so A, B, C, three samples, and they were anisotropically consolidated. So how can we say anisotropically consolidated? So this is the initial condition of the soil sample before shearing, okay? So he has done CU. So the soil was consolidated to this state. So we have a constant effective confinement of the soil. So this is the effective confinement state of the soil. And there is a deviatoric stress there as well. So static deviatoric stress as well. So this is a static deviatoric stress. All right. Or in some books it is written residual deviatoric stress. All right. It means the same thing. So this is the anisotropically consolidated. Isotropically it will be here. The soil state will be here. All right. So no shear stresses, no deviator stress. So that will be isotropically consolidated. Anisotropically because there is this amount of deviator stress. So then what he did, he sheared the sample, all right, and while shearing the sample, so A was very loose, B was very dense, all right, and C was somewhere in the intermediate state, all right. So A, what happened? If we look at the pore pressure generation, there was excessive pore pressure generation, and then it got stabilized, right? So up to this point, it has reached the point A here, right? So this is the liquefaction. So this Castro 1969, it defined as flow liquefaction. All right. So this, from initial state to the state A, this change in behavior, all right, so he termed as flow liquefaction. And at A, there is now a steady state of deformation, right? So constant velocity, constant volume, no change in pore pressure, no change in deviator stress, okay, or steady state strength of the soil. Now the deviator stress here at this point A is, he defined, Castro 1969 defined as the steady state strength of the soil. Right. So to cause flow liquefaction, obviously the deviatoric stress has to be applied. Deviatoric stress has to be somewhat equal to or maybe a little bit higher than A. All right. So that is the criteria for the flow liquefaction. Obviously, for the B, what happened at large strain, there was dilation, all right, and the pore pressure, it was towards the negative side, so del minus delta U. So pore pressure reduced. So as the pore pressure reduced, effective stresses increased, all right, and obviously there is no scope of liquefaction in this point. For the point B. Then the point C, what happened is, for certain amount of strain, what happened is it developed positive pore pressure. It developed a positive pore pressure. All right. So when there was a positive pore pressure development, so the effective stresses got reduced. Now effective stress got reduced, as well as you can see. So this is the residual static stress. All right. The steady state strength of the soil, all right, or the shear resistance of the soil dropped below that. So there may be significant amount of deformation in the soil as well, all right. But again, with more straining in the soil, what happened there? There occurred a phase transformation, all right. So here the soil, it started to dilate, and it reached this point here. So when the state increased from here to here, what happened? The effective stresses got increased, all right, and at higher, as we go on increasing, it will move, all right. So it will stabilize somewhere at this point. So now there is no scope of liquefaction. So this type of soil, that is where there is intermediate density, so they are prone to limited liquefaction as long as the soil is not allowed to strain significantly. All right, so the pore pressure may hold. So in that case, for that small brief period of time, the soil will undergo limited liquefaction, and obviously there may be deformation which may occur in the soil mass, right? But with higher amount of again deformation, it will again dilate, but that is obviously as Castro 1969, then Ishihara 1993. So they showed that it is almost up to 20% of strain is already reached by this state. So that is a significant amount of strain. Okay. Now, what he did, what Castro did was he tested various samples, all right, and at various confining pressures. So for various void ratios, initial void ratios, and various confining pressures, and then he arrived at the different steady state points, all right, and then he plotted the steady state line. So this is the steady state line. So he suggested that if a soil is above this line, then they are susceptible to flow type of liquefaction. Okay, and if they are below this line, they are not susceptible to flow liquefaction. But that does not mean that there may be they are not prone to cyclic mobility. Okay, cyclic mobility is totally a different phenomena. All right, so as we have seen here, so this limited liquefaction case, so a soil which is below the steady state line may undergo deformation or may develop poor water pressure during, and it may have significant amount of deformation through cyclic mobility. Right, we will see what cyclic mobility is. Right, so this is a flow type of liquefaction if it is above this steady state line. So what Castro did was to explain the condition of flow liquefaction. Right, he did some series of stress control tests. All right, so here one example is given. So here one sample is there, so it is loose and saturated sand. So he took a loose and saturated sand, all right, and it was isotopically consolidated. All right, loose and saturated. Okay, so 100%. So why isotopically consolidated? We can see here it is the initial starting point. So this is it is lying on the effective confinement axis. So isotopically consolidated. All right. So from there, so again he did CU test, right? But now what he did, he applied the stress incrementally and he went on applying, right? So when the stress was applied, for some amount of increment of stress up to the point B, right? So the pore pressure was developed. Obviously, this is in some manner like this, right? So there is some amount of pore pressure developed. So what happened is the effective confinement, so it reduced from this point to this point at this point B. All right, so here, sorry. All right. So it reduced from A to B. Now, obviously, if we see, so A is on the susceptible side of flow liquefaction. Okay, A is on the susceptible side of flow liquefaction. Now, as soon as it reached the point B, so there was a collapse in the soil structure. Okay, so there was a collapse in the soil structure. And the specimen and the sample, it became significantly unstable, right? So the particles of the soil, it started to reorient and rearrange, right? So when that happened, the pore pressure increased significantly, right? So significant increase in pore pressure occurred, and then it reached the point C. It reached the point C. So from here, as soon as it reached the point C, so there was no increase in pore pressure observed, right? So delta U is equal to 0. And the deviator stress at the point C was now defined as the steady state strength. Right? And this change of phase, all right, so and this, constant deformation at this point was termed as the flow liquefaction state. So where was flow liquefaction initiated? Flow liquefaction was initiated at the point B, right? At the point B, as soon as it crossed the point B, all right. So there was an, there was an irreversible, all right. So there was consolidation in the sample, like the particles, they compressed and they reoriented, and the state of the soil, which was initially at A, all right, the soil structure which was at A was totally now it was totally changed, all right, and from point B onwards there was excessive amount of pore pressure generation, and it reached the point C, from where on it continued to deform without any change of pore pressure at constant velocity, at constant volume, and it showed a steady state strength. So that point is the point C. Okay, so here we have the point A. So from A to B, right? So as the load was increased from A to B, so at B what happened? There was a the soil now it collapsed, all right, and then this is the liquefaction phase, right? So this is the liquefaction phase. So this state is the initiation of liquefaction, right? So the void ratio obviously remained constant, as you can see. That is because undrained condition, all right, and it moved from point A to B and B to C, and it reached the steady state line. So Castro, he did a series of tests for same void ratio sample A, B, C, D, E. All right, all were at the same void ratio, but at different confining pressures, effective confinement. right? So at different effective confinement. So E, the point at E, when it was, I mean, deviator load was applied, deviator stress was applied under undrained condition, all right? So it moved on to the point here. As soon as it reached here, again, as we have discussed in the earlier case, so there was a collapse in the structure of the soil, there was a reorientation, and there was liquefaction. Similarly, for the point D, from D onwards, as soon as it reached this point, there was liquefaction initiated. Then for C, what we see is C has an intermediate density. So C, it went on to this state. Now from here, there was limited liquefaction, but you can see as soon as it reached the steady state line, as soon as it reached the steady state line, there is a phase transformation. All right, so there is a small amount of phase transformation. So now the soil is actually now showing dilative behavior. All right, so the pore pressure. So if I draw the excess pore pressure for this point C, so it developed up to this point. All right, and then it changed sign. Right, so this from here onwards, so there is some amount of limited liquefaction here. So here there is some amount of limited liquefaction, but then there is a phase transformation from the steady state line as soon as it reached the steady state line, and then it went on to the steady state point here. So it showed the dilative behavior. All right, so C, it showed only limited liquefaction, whereas the sample D and E, so there was total flow liquefaction. All right, then what about A and B? So A and B, you can see it showed dilative behavior. All right, B, it showed dilative behavior. So dilative behavior means there is negative pore pressure generation. All right, so effective stress, it increased. Effective stress increased from A up to this point, steady state point in the sample. Right? So what Castro and in fact following researchers, what they did is they joined these points. All right, so they joined these points with the steady state line. So from the steady state line, they made a line perpendicular parallel to the confinement axis, effective confinement axis. Right, so this line here, and from here onwards they join the points. Right, and we have the flow liquefaction surface. So any point here, so they have to reach a point higher than the steady state point at this flow liquefaction. So as soon as they will reach here, so there will be liquefaction up to this point. So this is the liquefaction stress path. Right, so this is the liquefaction stress path. If they are below here, there will be dilative behavior. Right, and if they are somewhere here, maybe they will go there will be limited liquefaction. All right, and as soon as they will reach the steady state line, they will again revert back. All right, so you can see for different void ratios we will have different steady state points. So this is steady state point to this corresponding to this void ratio and this confinement. So we have this steady state point here. Right, so it will continue from here. So denser, as we go on to the denser state, right, so it goes on increasing. So that means liquefaction now, occurrence of liquefaction is reducing, right, because any point below this will dilate. All right, so if there is dilation, there is negative pore pressure generation, definitely there is no liquefaction. All right, so coming to that point, now how we define liquefaction, occurrence of liquefaction in this stress space. All right, in this stress space, how we define the occurrence of liquefaction. Now let us consider one sample, right? So that sample is at point A. So this is at point A. Okay. Now from the point A, it can be, so it is at a point, suppose, so we have a Davidric already static shear stress or static Davidric stress here. Right, so we have Q, so we plot the point A here, so we Q. Right, so no strain in the sample as of such, so strain is 0. So this is shear strain, right? So this is shear strain. So now either we can apply monotonic load. Apply monotonic load means we can increase the shearing of the sample. We can apply shear stress, incremental shear stress onto the sample, all right, under undrained condition, obviously, all right, under undrained condition. So as in these cases, so in these were isotropically consolidated, so it was here, so we have considered again anisotropically consolidated, because in the soil, in soil, as you have seen, so we have sigma v and we have sigma h and we have k naught, kp and ka and various states of anisotropy, right? And in fact there are some undulations in the ground, all right, or sliding sloping ground, all right, so various states of anisotropy. So we have this point A, the stress state, all right. So now there are two ways to liquefy this soil. Either we apply monotonic load, so if we apply monotonic load, so up to a point it will increase and then from there it will liquefy, all right, and then it will go to the steady state. So here, so in this stress path, how it will look, so it will increase in this manner and revert back to this point. So flow liquefaction is initiated. Flow liquefaction is initiated. Now this is obviously for monotonic case. Now similarly, without applying so much amount of stress, what we do is, if we apply a dynamic load, we can come to the same state and there will be liquefaction initiated, all right. So as we have seen in the previous slide, so the Morse circle, so the Morse circle, they move to the left, right, and I showed that if I draw the PQ stress path, it will look in this manner and it will oscillate in the failure line, right. So here what we can do, we can apply a dynamic load, all right, and there will be pore pressure. Obviously for the first cycle, first few cycle, it will oscillate here itself, right. There will be no pore pressure generation. As soon as there is pore pressure generation started, so it will move and it will reach here. So as soon as it reaches here, so we have flow liquefaction, right. So here we have flow liquefaction, static flow liquefaction, right, and here we have flow liquefaction due to the dynamic loading, right. So this is due to the monotonic loading, so we have the liquefaction here. So that is the significance of the flow liquefaction surface. Okay, so if we have a point here, we can initiate liquefaction. So this point here means it suggests two conditions. It suggests conditions of the effective confinement, all right, effective confinement and the Davidric stress in that sample. Right, so if suppose we have sigma v, there is an element, we have sigma h, so p, so sigma v dash and sigma h dash, so p dash is equal to sigma v dash plus sigma h dash by 2, right, and q is equal to sigma v dash minus sigma h dash by 2. So it is basically the diameter and the center of the Mohr circle, which is represented by this point in the PQ stress space. Right. So from this point A here, we can apply monotonic load. So if we apply monotonic load, so there will be an increase in the pore pressure. As soon as it reaches here, so the soil structure in the soil sample will collapse. It will start reorienting, and it will be a flow structure will be developed, and therefore there will be liquefaction. Now instead of incremental monotonic load, we can apply dynamic load, and when we apply dynamic load, there will be increase in the pore pressure. So for the first cycle, it will vibrate here itself. So as the pore pressure will start developing, the effective confinement, since p dash is equal to p minus u, so the effective confinement will start decreasing, and it will reach here this point. As soon as it reaches this point, there is flow liquefaction. Right. Now let us consider a point here. Now let us consider a point here. So if I apply monotonic load to this point, what will happen? It will go to the steady state point. So this is the steady state point. It will go to the steady state point. So what is happening is that there is a dilative behavior. Okay. So there is a dilative behavior. So definitely some amount of liquefaction will be there initially, maybe because there will be some amount of pore pressure generation basically, but we cannot say that it is liquefaction. Alright, or we cannot say that there is flow liquefaction developed. So there is a dilation here. So similarly, if the point is here, there is dilation here. Alright. So if it is here also, so obviously there will be some amount of limited liquefaction here observed. Alright, and it will come to this point here, and it will phase transform. Alright, so there will be phase transformation. So flow liquefaction only occurs if the stress state point and the void ratio, corresponding void ratio, they are above this, in this region, right, in this point, that is here. So this is the region. If the stress state is here in this region, we have the flow liquefaction, zone of susceptible flow liquefaction. All right. Now obviously the loading has to be undrained. That is an important case. The loading has to be undrained. Now similarly, if the point is here, so there may be three cases. All right, so one case is when there is an oscillation here, so there is no stress reversal in the sample. All right, and what will happen is that the state will reach this point and it will oscillate here. It will keep on oscillating in this range. All right. So basically what will happen is that the effective stress condition will stabilize at this point. all right, and the initiation of liquefaction cannot occur, all right. And of course some amount of displacement will occur, but cyclic mobility as such will also not occur because effective stresses are still there, all right, effective stresses are still there. Now if the soil is somewhere here, all right, and we apply a dynamic loading, so what happens, it touches the steady state line, all right, and it will come to the steady state point here and it will vibrate at this point. So there will be momentary, small amount of for fraction of, or few moments there will be instability which will be occurring, all right. So there will be some amount of instability, and there may be in that particular period. So since there is a high rate of loading, so in that small amount of time also there may be deformation which may cause significant amount of stress to any structure, or there may be significant amount of deformation, all right. So significant permanent strain may be developed in that case. Now in the third case, obviously what we discussed is, of course, in the triaxial test what we discuss is when the stress state is reversing, all right. So it is going up and it is reversing, and it is going up and reversing. So there is a, the shear in the sample is changing in the direction. So once it is in this direction, in the other the other this part of the cycle, it is in the other direction, right. So the sample is shearing in one direction, or one way in this half cycle, and in the other way in the other cycle, other part of the cycle. So that is what we discussed in the triaxial cell, and as well as the simple shear that we discussed. So in that case, the stress path will move in this manner, and it will move in this manner, and then it will oscillate here in the failure surface. It will keep on oscillating. So at this state, if you see at this state, when it is coming and reaching this state, again going and coming and reaching again this state, so this is a point where effective stress P dash is equal to 0, all right. So there will be a momentary period when the soil will behave as a liquefied soil, but now if we apply monotonic loading to this soil, what will happen is that this soil will dilate as it will try to reach the steady state, all right. So mainly it will try to reach, all soils will try to reach the steady state. So if it tries to reach the steady state from this point, obviously there will be dilation, and there will be some amount of negative water pressure generation, and the soil will ultimately stabilize, of course stabilize. But before that, before stabilization will occur, there will be already huge amount of strain deformation, shear strain deformation, which would have been occurred, and that would be really problematic for our case. Okay. So thing is that if you see here, if the point lies further away in this space, main point, the most important point in our discussion is, if the point lies further away from this point here, all right, so significant amount of loading will have to be occur to come up to this point, all right. So that is why the ratio is very important. So shear stress by effective mean effective stress, right? So if it is very high, that means it is further away from this flow line, right? So that is why the sample which we saw, though it was here, right? So it was very, the confining stresses were so high, the confining stresses were so high that it was very far away from this flow line, flow liquefaction surface, right? So liquefaction could not be initiated. And though this sample was here, it was somewhere maybe here, all right, or maybe here. So during that case, what happened is that during the loading case, so some amount of liquefaction occurred. So limited liquefaction occurred, all right, and that some, for even if for a brief moment, that amount of liquefaction, it is enough to cause significant amount of deformation, because 20% axial strain is, as the researchers have suggested, it is quite a significant amount, all right. So we see that as q by p dash is, it goes on increasing, the point goes on towards the right, all right, so further away from the flow liquefaction surface. So that means we are safe from liquefaction. As it is closer to the liquefaction surface, so small amount of now application of shear load is also cause liquefaction. Okay, so these are some important points to keep in mind, and in the next class we will discuss the important points, and of course how to evaluate the uh, whether there is chances of liquefaction or not. Okay, so in the next class we are going to discuss that. So